there's one more application that's quite important. You can see this, especially if any of you will later on work on the financial field or statistics. This understanding is good. So we want to find the average value, right, of a function. Right? Average value of a function. Value of a function, and then here I mean specifically we're talking about over inside an interval. So let's say you have a function right here, right? And then the curve for the function goes up and down, up and down. See what I'm saying? No? So a height, in our understanding now, a height on the x-axis, if we shoot up a height, right, and that's the function's value right there. The function value is represented graphically as how high it reaches, right? At that x value, how high it reaches up to hit the curve. You guys all agree? So that's why right there you can see that some height is lower than some other height, and some height is higher than some other height, right? So height varies all over. See what I'm saying? You got ups and downs, right? And that's why, think about this. You got a function being up and down all over, and then you restrict that into one interval from A to B right here. Okay? So we got height, we're experiencing all different various height up and down all over. So what's the average height? See what I'm saying? No? The average height, how high does it reach? Is that about here or is that about down here to be the average? We want to find that out. See what I'm saying? No? And that's the idea of what it says, the average value of a function. Okay? And so really it seems like a lot to explain, but and by the way, average value of a function gets that symbol F with a bar on top of that. We copy the symbol from the statistics people. So mean value, right? Mean value has an X bar. So when you got a whole bunch of data, mean value is X bar. So average value of a function, we use F bar for that. Okay? And so think about the idea right here. So we want to find the average height, right? What height is the average? Definitely it's not this guy, right? This guy is maybe like the highest in the whole interval here. See what I'm saying now? Not that guy, right? Because definitely that guy here seems like the lowest in the whole interval, right? So we want to find some average. So here's how I'm seeing it. And just think about the statistics, people. If they are, and you guys can do this too. If you're finding the average value of a set of numbers, how do you do it? You got a set of numbers and you want to find the average value.
Right, you just accumulate all of it and divide by whatever you have.
Yeah, accumulate all of them and divide by how many you have, right? And I like the term he would say, accumulate them all. Okay, so you got, now think about function's value. Some F1, right? Some height 1, some height 2, some height 3 right there. Accumulate them all. You guys following? And then we're saying divide by how many there are, right?
Yeah, however much you have.
Yeah. How many ever that you have right there? I agree totally. So that's the fundamental. That's the fundamental. You guys agree? But here's the problem. See, our function here, can we really count how many there are here in a problem like this? Especially when it comes to stripes. Right? We got infinitely many stripes. See what I'm saying now? We got infinitely many stripes, and then each stripe here got height up and down. That's why the accumulation works right here. The accumulation works right here inside an interval. Produces for us. The accumulation goes the interval from A to B of your function. That's to get the accumulation. The totaling up of all the heights you get, right? And then divide by how many there are. We really cannot know how many there are because there are infinitely many of those.
Just B minus A.
Yeah. We divide by the whole length B minus A right there. And that gives us a famous formula for calculating average value. You guys see the argument for that? Okay. And so, yes, the average value of your function will always be found by that formula. There you go. So you guys feel that naturally, right? So in this way right here, let's do one quick example. Find the average value of our function. Okay. So what's the average height, right? What's the average function output for the function here that's only on that interval? See what I'm saying? No? I mean, in a different interval, then we're going to have to apply the formula in a different interval. Right? But that's the main fundamental formula that we have for that. And so the work here is done as simply, as easily as just the average height is 1 over the interval where its final value being 1, right, minus the initial value being negative 1. Right? So 1 over the 1 over 1 minus negative 1. Right? And then we're doing that interval from minus 1 to 1 on your function x squared dx. So then we're setting up that accumulation with that. So that goes, so of course the average value comes out being 1/2, right? And it's a coefficient multiplied with the interval. And this interval is, the function is an even function, right? Pretty symmetric. So you can purposely turn that into a 2 times, right? The interval from 0 to 1, even though it was not like that initially, right? But it will equal. And then now x squared dx. The 2 cancel with that 2, right? So now all comes out to just being the interval from 0 to 1 on the x squared dx. Now it turns out to be just a 1/3, right? You guys have done the fundamental theorem of calculus all over these days already. See, the accumulation, this interval problem, I brought up very early in your learning, from 0 to 1 of x squared, right? And when I first explained about that, it was an area. See what I'm saying now? But for this problem right here, that interval came out, the 1/3 right there came out being the average height. Here's the picture. -1 to 1 here. You got your curve in that interval looking like that. See what I mean? So you got height all over. Some heights being 1, some height being lower than 1, right? You got all these heights and all these stripes being at different heights. So 1/3 is about right here. That height, whichever the stripe hits that height, right? See what I'm saying now? So note that height is the average. Because there are those above that and then those below that line there. So that the average height is right at the 1/3. Like that, right? 1/3. Yeah, no? And so, because of that, I was just now reviewing that little truth here. There has to be some point, right, that some x value in this interval that reaches the average value. See what I'm saying? Huh? So now we're going to lead that into the next understanding right here. It's still about the average value function. But and we're going to come to what's so-called the mean value theorem. So mean value is a different way of calling that the average value, right? You guys all agree? So in a more, in a more, how do I say this? In a more formal term, call that the mean value theorem. But now, if you guys making that connection with calculus 1 that you guys were learning earlier, there was also a mean value theorem back in your days of doing calculus 1. So the mean value theorem there was for differentiation. This is the mean value theorem for integration. Okay. The mean value theorem for integration. To make it clear with the mean value theorem we've done back in Calc 1. So that f of x might be a function continuous outside of the interval. I don't care, but at least it's continuous on the interval from a to b, some interval a to b. Right? But the mean value theorem now says there must be, as a guarantee, right? There must be a value c here that's staying inside of the interval from a to b. So when I'm saying there must be a c right here, a c, that means there could be more than one. Okay? There could be a value c inside of the interval from a to b satisfying f of c will equals the average height. So remember, to get that average height right here, it's a whole interval setup for that, right? It's a whole interval setup, but there will be a c inside of that interval so that the function value at c will equals the average height. Okay. So, or another way of saying that, f of c will equals 1 over b minus a times the integral from a to b function f(x) dx. That's a different way of saying that same formula here. But as a bigger picture, it just basically means there will be a value c in your interval where the function height reaches exactly the average height of your function. You know what I'm saying, no? Okay. So, admittedly, when I first started to learn about this, all textbooks gave this version here, all textbooks gave this version, and it's still the same like in these days here, but you know, as I went more majority to math, I realized the bigger picture is actually this. Okay? The idea is that you can always find a value or two inside of that interval where your function at those will hit the average height. See what I mean? Okay. So, right after copying down the theorem here, let's just put it into an example here. Call it now example 2. So the graphical result is still here. So let me now swing back to the theorem a little bit. You have to understand the intention of the theorem is only to guarantee that we should be able to find those c values that making your function reaches the average height. Yeah. That's all it's saying. That's all it's saying. Guaranteeing is the only thing that your theorem is doing. It's not naming out. This theorem is not naming out who that c value is, and that's why for this example right here, let's say we can see that our function, right? Our function is continuous on the interval from -1 to 1. Do you guys agree? Right? And that's all it needs to get. Right? Then from example 1 earlier, right? What do we know already? We know that the average height is 1/3, right? Okay? Know that from example 1, and this function here is for sure continuous. And so with that information, then we should, the idea now that should we even find that c? Yes, we should, because it will be inside of that interval. Then. It will be inside of that interval. That's why we should be able to go ahead and find it. Because think about it, there are other functions. I mean, it may not happen in your class right now, but someday it will. Who knows? One day you guys are going to end up with some more advanced math where your function can just simply be a discontinuous function like that. See what I'm saying? It gives you an interval, right? So maybe you can come up with some average height somehow, right? But with a function like this, the mean value theorem is going to fail. Because maybe you come up with some average height. Okay? See, it's these two constant pieces right here. If you average them out, you can still get an average height. See what I'm saying? No, but really, can you find a value? Which x value is this? Is that x right here? Is that when you reach that, right? Is this x? I'm talking about x here substituted into the right piece. It's not meeting with that height here. Or if you picking a c here, the c here belongs to that piece of the function, it's not hitting that height right there. So mean value theorem will fail when your function fails, when your function is not continuous inside of that interval. See what I'm saying? Okay. But then in our case right here specifically, our function is continuous, right? So we saw that, and the result earlier in the earlier example said that we got an average height here of 1/3. And so now you can already have some sense that, hey, there should be some c value, right? Some c value reaching the average height right there on the function's height. And so in that way, now we're going to go ahead and go further and find those c values. There could be more than one. And so now, think about it. On one hand, f of c, wherever that c is, inside the interval or outside the interval, wherever that c is, f of c means what? You're looking at c squared, right? You guys agree? But then we want c squared to equal, because the mean value theorem guarantees that c squared will equal with 1/3 to be the height. You guys agree on that still? So now it's just a matter of finding c. We solve this equation for c. C equals plus or minus square root of 1/3. That's it. And is this result consistent with our graph that we have seen earlier? Yeah, the height being 1/3, right? There are obviously two values. See what I'm saying? Two symmetric values in a way how our function looks. So that's how it's done right there. You have two values, and why do we have to do a problem like this? I guess you must wait for a later course, okay, where it has some real application. There will be real application of why you should locate those values giving you the average value. It may not happen here directly, yes, right? But it's worth it to pay attention to that. So again, the mean value theorem did not point out these values. It just guaranteed that those values should be able to be found inside of that interval. And then we're going to go ahead and use our the usual ideas again, right? Use our usual the algebra to find that. Right? But of course, think about if you have a problem like this without the average value previously found like this, then you have to start from scratch, calculate the average value first. See what I'm saying? Huh? And then set that value equal to f of c and then solve for c. Are you understanding what I'm trying to say? Yeah? All right. So, and that's pretty much all for average value of a function like that. Okay? Any question that we have that you guys have for me?